Okay, next up is nomenclature, which is the same as naming. Sort of how do we look at a compound and come up with a systematic name where we have these rules so that if a scientist says, hey, I have sodium chloride, another scientist understands those same rules and understands the actual atoms that are involved in that bond. It's about just establishing some sort of framework whereby when we hear a certain word, we know what the word means. All right. Just a quick little review again. All right. If you go back and look at slide 18 and slide 19, the big thing with naming, just like the last video, is all about separating ideas based on whether a metal's present or not, whether you have ionic bonds or whether you have covalent bonds. It's our very first step. So again, go and review those slides, look at the forms that are shown, understand that there's a different process in forming in terms of forming ionic bonds versus covalent bonds, all right? And because there's a different process for each, and you'll see that in the pictures that are shown, because there's a different process for each, there's going to be different rules for how we name ionic and covalent bonds, right? And it's all about ionic and covalent compounds, right? It's all about just making sure we understand that the processes are different, and then we have to be able to interpret information from the periodic table, okay? So where we're going to start is we're going to start with ionic compound naming. And the first thing we want to do to make sure that we're using the correct naming rules is to make sure we actually have an ionic compound. Now, from the last video, we know that what we look for is a metal, okay? So as soon as you see a metal, you know you have an ionic compound, and then you're going to follow these rules, okay? I'm also going to put this caveat here now, though. We could also have something that acts like a metal, all right? And what we're going to do in terms of identifying something that acts like a metal is there are going to be some things that we talk about in this section that we know are positive. And if something has a positive charge, remember all the metals that we were referencing on the periodic table, they would have a positive charge as well, all right? So if something has a positive charge, we're going to say it acts like a metal, and so then it definitely is involved in an ionic compound. And that kind of makes sense because if it's an ion, the only way it can bond is through an ionic compound situation. Here are the general rules for how we name ionic compounds, okay? You use the full cation name first, so you kind of name the metal, all right? And then you do an anion root plus IDE, and that's it, okay? There's a lot of inferred information here. There's a lot of sort of assumption that you understand the structure of the periodic table to actually come up with this name, all right? That's all the information that you need to do and to start naming ionic compounds. So let's go to some examples, and let's go back to this common example of sodium chloride, right, NaCl. Just always kind of go back to this because you're probably familiar with sodium chloride already, okay? And you understand what its name is. But now let's see how this actually fits with our general naming rules, right? We identify first that we have an ionic compound because I see that Na is present, and Na is in group 1A, and I know that's an alkali earth metal, right? I use that full name first, right? So you literally just kind of say sodium, right? Then I look at the anion, and the anion is chlorine, but what you do is you change the end of its name, right? You're not going to say sodium chlorine, right? What you're going to do is you're going to use the anion root, right? The anion root, which would be chlor. And then at the end of the word, you add IDE, right? IDE. So if you can kind of get sodium chloride and see how it fits with our general rule, you can name pretty much any ionic compound, all right, with some caveats that we talk about in a bit. Let's take a look at K3P, all right? So if I look at this, the first step is to identify, do I see a metal? And K is potassium. And again, if you look at potassium, it is in group 1A. So it's a group 1A metal. Yep, a metal's present. So what kind of bond do I have? I have an ionic bond. I'm going to use my ionic compound naming rules, okay? So P is phosphorus, and it's a non-metal, okay? So here's what we have to do. We have to follow our general process. I take the metal name and I write it down. Potassium, right? This is phosphorus, but I know I always have the ending of IDE for these types of compounds. So I'm going to label this as phosphide, right? So cation first, anion root, end with IDE, potassium phosphide, right? Now, why is potassium phosphide K3P? Well, if you look at K is +1. If you look at P, because it's an alkali metal, right? It's in group 1A. P is in nitrogen's group. P is in 5A. And P then, we know from our periodic table discussion, is a -3 charge. Well, now you can kind of see why we need 3 Ks. How am I going to get a balance of charge here, okay? When I bring these guys together, I actually need 3 different pluses to cancel the -3 of the phosphide. Now, that's not in the name, okay? Notice, potassium phosphide assumes that you know, and you can look at the periodic table and say, oh yeah, phosphorus is -3, and K is +1, so I know there would be 3 Ks to 1 P, right? That information is not in the name because, again, it's assumed that you can look at the periodic table and know that information, okay? So with that idea in mind, let's go the other way. So it's important to know how to go from a formula to a name, but what about going from a name to a formula? It's a bit harder, okay? What we have to do is look at the periodic table and do that charge balancing that I just mentioned now, right? What about calcium bromide? So now going in the opposite direction, we see that we definitely have a ionic compound. I look on the periodic table and I see that calcium, which is Ca, is in group 2A. So calcium would have a charge of +2. Bromide is not on the periodic table, but bromine is. So remember that ending IDE, now we kind of take it off and we think about something that would have the same root. So brom sounds like bromine. Bromine we find on the periodic table as a halogen. And if it's in group 7A, it has a -1 charge. Then what you do is you think about bringing these spheres together so that there are a balance of charge. And so if I have a Ca that's +2, how many Brs do I need to balance out that charge? 2. So calcium bromide, based off of balancing charge, is CaBr2. Okay. What about beryllium, which is Be? Let's do something that's easier to spell. About barium oxide. All right, barium oxide. Again, we look for Ba here. Ba is in group 2A, so it's going to have a +2 charge. Okay. Oxygen, okay, is in group 6A, and we memorized, or we know from our last video, that in group 6A, oxygen's group, everything's -2. So what do we have to sort of balance these guys out? Well, Ba is +2 and O is -2, so really all I need is one Ba and one O to come together to get something that's completely balanced in terms of charge. This +2 touching this -2 gives me something that's overall neutral, so I get BaO. Okay, so we just kind of use this pattern, we just follow this idea over and over again. Let's do one more example. Aluminum, let's do aluminum sulfide. How about that? Aluminum sulfide. You can get a little bit tricky situations, and I'm going to teach you like a quick little thing you can do in such situations. Aluminum's in group 3A, so Al, definitely a metal, definitely to the left of the staircase, all right? It would have a charge of +3. Sulfide, that kind of sounds like it's coming from sulfur, which is in oxygen's group, so it would have a -2 charge in ionic compounds, all right? So I have to think about how 3s and 2s can balance each other out. You kind of think about a common factor. Now, a high school way of doing this, which is okay to do, but you just make sure that you have the simplest form, is to take these guys and switch them up, right? And so what I mean by that is aluminum sulfide is actually Al2S3, But that makes sense from a balancing charge standpoint because a common factor between 3 and 2 would be 6. So how do I get to 6 with a plus 3? I multiply it by 2. How do I get to 6 with a minus 2, right? I multiply it by 3, right? I would have a plus 6 and a minus 6 that would give me an overall neutral charge, right? The reason I said that this was like the high school way of doing things, you just have to be careful. If you go back to something like calcium oxide, which we did, right? You don't ever want to write these, right? It's all about balancing charge. That's the way I like to sort of present it. Because if I do this and I write calcium oxide as Ca2O2, right? That's actually incorrect. Because if you look at this, one Ca balances one O. So what you would do in this situation is you say, oh yeah, Ca2O2, that doesn't make any sense at all, right? I don't need 2 calciums and 2 oxygens to balance charge. I just need one of each. Just kind of be mindful of that, be aware of it. And just make sure, like I said, that you always kind of simplify things down if you do want to do this little trick. But again, seeing the charges is going to be a lot more beneficial for future things that we do in chemistry. So always kind of just realize that this is all about creating structures that balance charge completely. Okay, so then what about transition metals? So our rules need amendments as we go into ionic compounds with transition metals. So this is still underneath ionic compounds, but what if there's a transition metal? Because remember, everything about the discussion we're having is we know charge. And so we can just go ahead and write these formulas. We can just state these real simple names because we know how to charge balance. Well, with transition metals, you don't know what the charge is, and there could be multiple charges. And so what we have to do is we have to add information into our name. Because iron is sometimes +2 and +3 and +4. And same with cobalt, same with silver, because there are various charges there and there's no set and true pattern in that transition metal block. The information that you add to our name is we're going to use a Roman numeral to indicate the metal's charge. You actually, because charge is now ambiguous, right? Because it's something that we don't definitely know, we have to include it into our name, all right? So it's just one extra thing that we do when we see a transition metal in our compounds that we're trying to name, right? So as an example, these two are ways, these two are definite compounds, definitely 2 different ways that copper, which is Cu, and sulfur can combine, okay? So they're both ionic compounds because I see that there's a metal present. Now, right, your extra check is, hold on a second, is that metal a transition metal? And if it's a transition metal, if the answer to that question is yes, then you know you're going to include charge in the name. And you only do this for transition metals, okay? So for example, up here, we use our same logic flow, right? Same ideas here. They're still ionic compounds. They're still overall neutral. So this S, right? What's its charge always? Excuse me. S always has a certain charge no matter what. There's no ambiguity with S. S is always -2. Well, for this case with copper, right? What must the charge of each copper be? Well, copper, there's 2 of them. So how can I get 2 things to cancel a -2? Copper must be +1, right? So that's why we need 2 coppers and 1 sulfur to make this compound, right? So the name then reflects that copper is +1. We go copper, just like we would any other normal compound, but then we're going to use a Roman numeral here to indicate that it has a +1 charge, and then we finish as we do other compounds. So it's not copper sulfide, right? This is copper 1 sulfide, and that 1 indicates the charge of the copper. okay? Same thing here. We can kind of look at this. Oh, if we would just use normal naming rules, this would be copper sulfide and this would be copper sulfide, but these are not the same species. This has 2 coppers and this only has 1 copper, all right? So again, we need that extra information there. So we use our ideas. S is always -2. In this case, what must copper's charge be? Copper must be +2 to balance out that -2. So then how do we name this guy? This one is named copper 2 sulfide, right? Copper 2 sulfide. So for transition metals, we need this extra information. We need to put a Roman numeral that indicates the charge of the metal, all right, in our name, right? And now we see, okay, yep, this is definitely a different name, so it's a different compound. Copper 1 sulfide, that tells me there's 2 Cus stuck to an S. Copper 2 sulfide tells me that there's a Cu and S stuck together, okay? Let's go in the opposite direction. Another example. Oops, sorry for bumping that. Vanadium is V. Vanadium can have a whole bunch of different charges. Vanadium 6 oxide is an example we'll do. And then let's do nickel 2 chloride. Right, nickel 2, or let's do fluoride just for something different. Now we've seen chlorides before. Okay, so I look and how do I know this name actually involves an ionic compound? I see names of metals. Now these names occur as elements that are in the transition block. And I can kind of see that they're transition metals because look at this information that's given to me here, right? Now, this Roman numeral 6, so that tells me that vanadium, which is V, is +6 in this compound, right? It's given right in that name, right? Oxygen, right, which would give me an oxide, is always -2, right? So if you think about this, oh, this is +6. How many of these -2s do I need to balance out that +6? I would need 3 of them. So vanadium 6 oxide is VO3, right? VO3. Nickel 2 fluoride, nickel is Ni. It's also in that transition block. The 2 indicates that it's a +2. Fluoride, fluorine, F is a halogen and it has a charge of -1. All right, so in this case, oh yeah, nickel's +2. I would need 2 of the F's to balance it out, right? It's actually kind of a little bit easier to go from a name to a compound with transition metals because you actually have the charge there. It's given right in the name. You don't have to know anything about the periodic table, right? Oh yeah, I want to do one other example. Just remember tin and lead are also considered transition metals. So tin is Sn. So let's look at like Sn. Let's name this one. Let's do Sn. SNI4, and then let's look at going to a name. From a name to a formula with lead to nitride. All right. So let's do the top example together first. Sn, I identify it as a metal. It's not in the transition block, but I've stressed it again and again. It's treated like a transition metal, so we're going to name it like a transition metal. Tin can actually acquire different charges. I, though, the anion it's attached to is definitely a halogen. So I, for sure, has a -1 charge. Okay, so then we have an Sn, which we don't know its charge, but we have 4 I minuses. Okay, well now I know what Sn's charge must be. Sn must have a +4 charge to balance out with the 4 I minuses that we have. So then this must be tin 4 iodide. All right, tin 4 iodide. Again, including the actual charge in the name, because tin is treated like a transition metal. All right, let me write that in the Roman numeral again. Tin 4 iodide. All right, tin 4 iodide. So let's go in the opposite direction here with lead 2 nitrate. Again, even though lead is technically not in the transition block, it's still a metal that's treated like a transition metal. This tells me that lead, which is Pb, has a +2 charge, right? Now nitride ends in IDE, so it's coming from the periodic. Okay, this is nitrogen. Nitrogen's group is 5A, and we learned that group 5A has a -3 charge, right? So again, it's one of these situations where we're hitting +6 and -6, right, to balance out the charge. And what we end up with is Pb3 and 2 to get something that's completely balanced and neutral, but also a bunch of pluses and minuses stuck together. All right. So this is our introduction to ionic compound naming. There's a couple other instances of complication that we'll talk about with respect to ionic compound naming in the next video.